So before we move on into the various application of definite integrals, I would like us to kind of remind ourselves on an area as an antiderivative or antiderivative as an area, right? So and also kind of add the fundamental theorem of integral calculus and how it's related to or it's same as definite integral or antiderivative as an area. So basically in general, the general method to find the area under a graph, for example, a graph y equal to f of x between the points x equal to a and x equal to b is given by the following important theorem, and that is the theorem of or the fundamental theorem of integral calculus. So for instance, let f of x be a continuous real value function on the interval a and then what b. As you have learned already in SHS, you know when something is like you have x and what y. So it means that the a represents the x value and then the y represent the b represent the y value. So let x represent a continuous real value function on the interval, which is what a and b. So based on that we can say that the integral of a to b of the function f of x dx, right, with respect to x is equal to the integral. So assuming that if f of x is the function, it means that its integral, right, the integral of this f of x is the same as the capital F of x, assuming this is the notation that we are using. So based on that, we are going to get the integral of f of x dx is equal to f of x, and then remember the limits, lower limit and then upper limit, and therefore our final answer is going to be f of what b, the upper limit, minus f of what a, the lower limit, where this f of x, as I've explained earlier on, is the antiderivative or any antiderivative of the function which was given in the question f of x, right? So that is it. So that's the meaning or the interpretation of the fundamental theorem of integral calculus. So basically this kind of notation, let me pick up some through here. So as you can see, this kind of notation over here, the capital F of x, with the limits, lower limit a and the upper limit b, is just a shorthand to substitute these values of x, which is x equal to a and x equal to b, into this particular function, which is the integration that we found, and also subtract it from its counterpart. So basically it's going to be the substitution of the upper limit into the function minus the substitution of the lower limit into the function. So we should note that any antiderivative, we should note over here that any antiderivative of the function f of x will work in the above theorem. Any antiderivative of the function f of x will work in the above theorem that we have discussed right now. So if we have two different maybe antiderivatives, maybe f of x and g of x of f of x, then they must differ by a constant. Maybe g of x equal to f of x plus c for some constant value c. I'll try and use some examples to kind of explain this so that you can get this one very well, or you can get this one very well. So basically, let's see something here. Let's see some cool example over here before we come and solve these examples. Before we can come and solve this example, I want us to just see some cool examples around. So basically, let's pick this example. We should find the area of the function, right? Find the area under the function find the area under the function f of x equal to x squared plus 1 dx. The interval x equal to 0 and x equal to 5. So this is the question given. So you find the area under the function f of x equal to x squared plus 1 all dx, of which x equal to 0 and x equal to 5. So this is just a simple question. So based on the explanation I gave earlier on, when I was explaining the fundamental theorem of integral calculus, the shorthand for this is given by the integral of the lower limit 0 to 5, and then the function value, which is x squared plus 1, and then dx. So this is the shorthand for all these plenty things over here. So based on this, you can start evaluating them. So in finding the integral of this function over here, x squared plus 1, we are going to get x power what? 3 over what? 3, and then plus what? Integral of 1 is what? X. So based on that, don't forget that we have a limit which is what? 0 to 5, and therefore, as the fundamental theorem saying, we do the upper limit, we substitute the upper limit into the integration we have done and subtract it from the substitution of the lower limit into the integration that we have done. So this is in simple terms. We are going to get 1 over 3 multiplied by 5 power 3, which is the substitution of the upper limit. 5 power 3 over, 5 over 3, because we have already bring this one out, right? So let me write it again. 1 over 3 multiplied by 5 power 3 plus 5, right? And then this is the upper limit minus the lower limit, which is what? 0 power 3 over 3, right? Plus 0. So you know that all these ones will go to 0, and this one, when we do it, we are going to get 125 over 3 plus 5. And at the end of the day, we are going to get 46 whole number 2 over 3. You can also try to express into decimal form. You don't have problem with that, right? So this is a simple illustration using the integral fundamental theorem of integral calculus. So since we now understand and we have done a little bit of recap on the area as an antiderivative, let's try and solve this area example that I have two area examples for you. You can pause the video and apply the fundamental theorem of calculus, integral calculus, to do it. So let's see something here. So now suppose that y is the profit per unit or per mile traveled, and x is the number of miles traveled in thousands. So the question is, we should find the area under y equal to 1 over x over the interval, which is 1, 4, and then we should interpret the significance of this answer, right? So basically the same thing, applying the fundamental theorem of integral calculus to find the area under the curve, which is in this case the application that we are coming to solve, application of the area that we are coming to solve. It's being like the short, first of all, just write the shorthand first. Let's type the solution. So the shorthand for this whole question that has been typed over here, it's summarized as integral of 1 to 4, and then the function is what? 1 over x, and the whole thing is what? With respect, we are integrating with respect to x. So this is the shorthand for this. So now that we have the shorthand for this, what do we do next? Applying the fundamental theorem of integral calculus, we just move ahead and integrate the function, and we are aware that integration of 1 over x is ln x, right? Integration of 1 over x is ln x, and therefore we are going to get ln x, and then from ln x we should remember that our limits are 1 and 4. So based on that, we are going to get, applying the fundamental theorem of integral calculus, upper limit minus lower limit, and therefore we have ln of 4 minus ln of 1, and ln of 1 is going to give me 0, and therefore my final answer is going to be ln of 4. So when you take your calculator to type the ln of 4, you are supposed to get something like 1.39 as approximation, or you can go ahead to write up to maybe 4 decimal place, which is 1.3863. Let's look at the last example as we remind ourselves area as an additive derivative, so that we can move ahead to the different applications of definite integrals. So the last example, it's that we should find the area under y equal to 1 over x squared over the interval 1 and b. So as I said in my previous video, right, the integral of 1 over x is the ln x, right? But if you have an integral of 1 over x squared, is not ln x squared, right? It's totally wrong. You need to apply your law of indices to kind of help you simplify it. So based on this, what you can do is, first of all, I said write the shorthand, which is equal to the integral of 1b, which is the 1 is the lower limit, and this one's the upper limit, right? So based on that, 1 to b, and then our function is going to be 1 over x squared, and then put it in with respect to dx. So now this is our shorthand for this. So based on that, we continue to do our integration, and we are going to get or let's simplify it first. We are going to bring the x squared up, so it's going to be x power negative 2, right? So the integral of x power negative 2, and then that's the integral of 1 to b, and then with respect to dx. So from here you can continue to integrate it, and as usual what you can do is x power negative 2, right? X power negative 2, so this place is not coming, right? So let's write here. So in all, we are going to get x power negative 2 plus 1 over negative 2 plus 1, right? And don't forget that we have our limit here, which is 1 to b, and therefore in simplifying this, we are going to get x power negative 1 over negative 1, and then we have 1 to b, and therefore in applying the fundamental theorem of integral calculus, we are going to get negative 1 over b minus, right, that's negative 1 over b, that is the upper limit, and then minus the lower limit, which is what, negative 1 over 1. and therefore this one will give us positive, and at the end of the day we are going to get 1 minus b 1 minus 1 over b. So this will be your final answer. So let's quickly go here. I forgot to get an interpretation of this. So now we got a value of 1.386, and when we come to the question, we were told that this value is in thousands. So if this value is in thousands, we are going to get 1386.3. So it's in dollars, right? Yeah, it's in dollars. So we can say that considering the unit which is in dollars, we see that the area represents a total profit of 1,386.3 when the miles traveled increases from 1,000, because 1,000 miles to what? 4,000 miles, because the upper limit was 4. Right, so that's the simple interpretation of the answer that we got from there. So thank you for watching, and see you in my next video under application of definite integral.